Hello students. So in the last video we saw what an equivalence relation is. That is three conditions you have to satisfy first, that is reflexive, symmetric and transitive. Okay, now let's solve some examples. That is, I'm starting with exercise 1.1. Okay. We'll do some questions. Okay. So first question is, you have to determine whether each of the following relations are reflexive, symmetric and transitive. Okay, so the relations are defined. You have to first find the elements in the relation, okay, and then you have to go for reflexivity, transitivity and symmetric. Okay, so let's write first question, question number 1. First sub question. So the A set is given to be 14. Okay, and this set is defined as, relation is defined as set of all x comma y such that 3x minus y is 0. Okay, so you have to first find the relation. Okay. So R set, now if I take x equal to 1, okay, so 3x equal to 1 minus, to get 0 you will need 3, right? So first element will be 1 comma 3. Okay, this you can find by like this also, that is you have to convert that equation. So this is 3x minus y equal to 0. So this is minus y equal to minus 3x. Okay, so y equal to 3x. Now you have to put the values of x so that you will get values of y. Okay, so when x is equal to 1, you will get y equal to 3. When x is equal to 2, you will get y equal to 3 to the 6. When x is equal to 3, you will get y equal to 9. Then when x is equal to 4, you will get 4 3s are 12. And 5 3s are 15. Okay. So this element is not there here because A is a set up to 14, right? So here comes 15, so you have to remove this. So you have to stop here only. Okay. Now let's check for reflexivity. Reflexive. Okay, so here the elements of the type 1 comma 1, 2 comma 2 are not there, right? So 1 comma 1, 2 comma 2 till 14 comma 14, they does not belong to R. So R is not reflexive. Okay. Then second, I have to check for transitivity. So if I take check for symmetric, so I am taking element 1 comma 3 belongs to R. Okay, but 3 comma 1 does not belongs to R. So this implies that R is not symmetric. Okay, and third, you have to check for transitivity. So take elements 1 comma 3 and 3 comma 9. Okay, 1 comma 3 belongs to R and 3 comma 9 belongs to R, but 1 comma 9 does not belongs to R. So this implies that R is not transitive. Okay, so it is not an equivalence relation. Okay, let's see the second question. So R is defined to be set of all x comma y. Okay, and it is defined on the set of natural numbers. Okay, so y is equal to x plus 5 and x is less than 4. Okay, so the condition given is this x belongs to set of natural numbers and x is less than 4. So set of natural numbers start from 1 and x is less than 4. So our choices for x will be 1, 2, 3. That is 1, 2, 3, right? So let's find this. So when it is 1, you will get y6. When it is 2, you will get y7. When it is 3, you will get y8. Okay. Now let's check for reflexivity. Okay. So hence since 1, 1, 2, 2 and 3, 3 and so on does not belongs to R, we can say that it is not reflexive, right? It is not reflexive. Secondly, symmetric. Okay. Take one element 1, 6 belongs to R, but 6, 1 does not belongs to R. So hence it is not symmetric. Okay. Now third one is you have to check for transitivity. Now look here that here 3 elements are there, right? 1, 6, 2, 7 and 3, 8. Now if I take 1, 6, okay, belongs to R, there is no element such that 6, something is there. Okay, this element does not belongs to R. So there is no question of finding 1, something belongs to R, right? In this case we write this to be transitive because there does not exist any pair such that any A, B and B, C belonging to R. We don't have A, C belonging to R. Okay, so if you have A, B belonging to R, okay, but B, C is not there and A, C is not there, you can directly write it is transitive. Okay, this becomes transitive. Okay, so there is no pair in R such that A, B and B, C belongs to R, so we need not look for the order pair A, C. Okay, so it is transitive. If you have only one element in R, okay, suppose it was 1, 6, then this also becomes transitive. Okay, because 1, 6 is there, but 6, something is not there, and also 1, something is not there, right? So we can write this as transitive. Keep that in mind. Okay. Let's solve the third question. Third question, A is given 1, 2, till 6, right? And R is given to be set of all x, y such that y is divisible by x. Okay, so y is divisible by x, so find R first. Okay, you will get many elements. Okay. So for reflexivity you can check for 1, 1, 2, 2. Obviously the number, both the numbers are divisible by each other, right? So we can say that these elements are going to exist in this R, right? So we can directly write that R is reflexive since x, x belongs to R for all x belonging to A. Okay, now let's check for reflexivity. symmetric. Okay, take one element. Say suppose I am taking element y is divisible by x. So the number y should be divisible by this number. So 4 is divisible by 2, right? So this belongs to R. Now 4 is divisible by 2. If I take the symmetric element, that is 4 comma 2, is divisible by 4. No, this doesn't happen, right? So if I take suppose 9 is not there, so 6 you can take. 6 is divisible by 3, but 3 is not divisible by 6, right? So this is not symmetric. Okay, so you can write taking 2 comma 4 belong to R, which implies 4 is divisible by 2, but 2 is not divisible by 4, which implies 4 comma 2 does not belongs to R. This implies R is not symmetric. Okay, third, you have to check for transitivity. Take one element, okay, from R. Suppose I take one element, one comma 2, and other element is 2 comma 4. So I can take 1 comma 4, right? So this is enough. So 1 comma 2 belongs to R. This implies 2 is divisible by 1. Okay, and 2 comma 4 belongs to R, which implies 4 is divisible by 2. So this implies so we can take 1 comma 4 belongs to R, okay, because 4 is divisible by 1. So it is transitive. Okay, fourth one, R is given to be x comma y, so x minus y is an integer. Set of all x comma y such that x minus y is an integer. Okay, so integers are what? Numbers positive and negative, right? So let's start proving this. So it is a generalized form, right? So we can take examples also. So if I take for 1 comma 1, say 1 comma 1, 1 minus 1 is 0, and 0 is an integer, right? So it is true for all the pairs, okay, which we can form using the integers. 1 comma 1, then minus 1 comma minus 1. Okay, again you will get a 0. It is an integer. Okay, so for reflexivity, this is true. So x comma x belonging to R, we can say x minus x is 0, which is belonging to Z. So this implies R is reflexive. Okay, for all x belonging to R, integers. Then for symmetric, take one element, say x comma y, or take one element, say a comma b, belonging to R. This implies a minus b is x minus y should be an integer. A minus b belongs to z. Okay. A minus b belongs to z. Okay, so this implies that if I take a negative of this number, means if I take a negative outside, so this will be b minus c, right? Now this also belongs to an integer because negative numbers belongs to integer, so we can say that b minus c belongs to integer, so we can say that b comma c belongs to R. Okay, so it is symmetric. Now let's prove for transitivity. Okay. Take one element a comma b belonging to R and another element say b comma c belonging to R. So a comma b belonging to R implies that a minus b belongs to set of integers, and this implies that b minus c belongs to set of integers. Okay, so if I take a minus c, because I want a comma c to be belonging to set of integers, right? So a minus c, this I can write it as a minus b plus, if I add these two elements a minus b and b minus c, you will get a minus c, right? So this is addition of two integers, you get a integer. So you can say that as a minus c belongs to set of integers, a comma c belongs to R. Okay, so this is transitive. Okay.